Charles River Phosphorus Sensor, subject to change, GE 1502, spring 2018, 8 a.m. Zoha Rana, Emily Fesco, Jack Karras, and Luke Kim.
Very few citizens of the Boston area are aware of the high toxicity of the Charles River. Many of these people walk by the river or pass by it on their daily commutes and admire its beauty, but they do not know that the high levels of phosphorus present in this body of water threaten its ecosystem or make it unsafe for them to swim in. The real problem is that these citizens don't have access to this information. It is extremely difficult to find the phosphorus level in the river without extensive research. Subject to Change sought out a way, by designing an improved SparkFun system, to display this data using a calibrated turbidity sensor instead of a photoresistor and make it readily available to the public.
The first article shown details that excess phosphorus enters the waterway due to stormwater runoff, discharges from wastewater treatment plants, and combined sewer overflows, leading to higher phosphorus levels than preferred. The second article shown describes how water quality monitoring usually involves either one of a singular system that checks pH, conductivity, etc., or a sensor probe made to detect specific contaminants. Our system is more like the second kind of specialty sensors described.
There are many products currently in the market that can assist in measuring the phosphorus levels in water. One such example is the hydrocycle phosphate sensor. While a very sophisticated, efficient, and durable device, this sensor is not practical for the average person. Not only is the sensor very expensive, but it takes a long time to deploy, and it's meant to stay in place for months. The only way for data to be extracted is by bringing the sensor back up and downloading data from it. The average consumer ultimately has no way of accessing this data unless it ends up being published.
Because our system lives in the water, it can relay live data back efficiently. The primary problem that we hope to solve with this project was communication of this data, allowing for consumers to make smart, informed decisions regarding being able to interact with their surroundings. The sensor detects the turbidity of the water in NTUs, and with our conversion factor of NTU to phosphorus specific to the Charles River, we are able to obtain live phosphorus level readings. This data can be seen on our LCD screen and on the serial plotter on Arduino.
Our project is composed of two separate systems, each containing various laser-cut parts. The sensor is housed in a 3D laser-cut acrylic box. The acrylic is sturdy and waterproof, which is necessary as this part of our project operates in the river. The display is housed in a 3D laser-cut wood box. The wood is sturdy and durable, but more practical than acrylic as it's less expensive and doesn't need to be waterproof.
The turbidity sensor is the primary input in this project. It lives in the water system and collects live turbidity levels of the water. Our second input device type is buttons. The push buttons are used to control the LED lights. The red button turns them both off and the green button turns them both on. The LCD screen is one of our output devices. It displays the translated phosphorus levels that are obtained from converting the turbidity values from the sensor. Additionally, we have two LEDs. The green LED turns on when the phosphorus level is determined to be safe, which is under 0.0238 milligrams per liter, and the red LED turns on when the levels are above that value.
We would begin by including the library needed for the LCD screen and initializing the variables and pins to be used throughout the code. The LED and the LCD would be set up as outputs and the buttons as inputs. In the next loop, we would do the calibration calculations to go from the red voltage value to the turbidity value in NTU and to the phosphorus value in milligrams per liter. Then the phosphorus values would be outputted to the LCD screen, and if the level read from the sensor is greater than 0.0238 milligrams per liter, which is the threshold for phosphorus in the Charles River, the red LED would turn on. Otherwise, the green LED turns on.
Our goals were to design user-friendly, inexpensive, reliable, environmentally friendly, and lightweight project. Also, one of our value-sensitive design objectives was to warn citizens about the chemical composition in the Charles River, so that there is a positive effect of safety on these communities. We were able to successfully accomplish these goals by making a control box to display the phosphorus level easily, by making the project under the budget, by using our new turbidity sensor to make data reliable, and by using acrylic to make our project environmentally friendly and lightweight.
Our desired functions for this project were for to detect and output phosphorus levels and to communicate through an LCD screen and through an easily accessible website. Our project certainly detects the phosphorus levels, however we only accomplished one half of the next function. We were able to output data on the LCD screen, however we were not able to transfer our data online. This is due to the fact that the SparkFun Wi-Fi module is a very difficult part to use and understand. We spent weeks trying to get the module to function, and even with the help of SparkFun experts in the FYELC, we were not able to figure it out.
Our constraints for this project were to spend less than $50 additionally, smaller than 12 by 18 by 12 cubic inches, and at least 60% original. We spent $26 additionally, and our project is smaller than 12 by 18 by 12 inches. Also, the container for our electronics were designed completely by us, and the Arduino code was mostly written by us, so we were able to meet all our original constraints.
After overcoming many difficulties with the use of a new DF robot turbidity sensor, errors in its calibration, and struggles with using a Wi-Fi module or radio transmitter and receiver, we were able to create a system that conveys the phosphorus levels in the Charles River to the citizens who are in dire need of this information. We were able to continue our project from last semester, significantly improving the user interface, the display of information, and the accuracy of the readings. We learned that it is extremely difficult to understand a highly undocumented product like the Wi-Fi module, and we learned that it is difficult to go from a sketch of a system to laser cutting and building the system. We learned that there are many more ethical situations to consider when approaching an environment from the engineer's perspective. For example, when implementing this system in the Charles River, we had to consider further disturbance of the ecosystem if we were to place this in the river. We struggled for weeks attempting to make our system wireless, and even with the help of professors such as Don Goldwaith, we were not successful. We learned that it was okay to not be successful with some elements as long as we had backup plans. As a guild, we are most proud of the work and dedication that occurred as we tried to make the Wi-Fi and transmitter and receiver, and how we were able to make a backup plan just in case the work didn't come out as planned.